thank you everyone for attending to my talk. I'm José M, Lendínez, a PhD student from the Institute of Material Science of Madrid, and today I'll be talking about our current first principles study of the antiferromagnetic Janus Monolayer MnTeI. So this work has been done in strong collaboration with Mikhail Otrokov from the Institute of Nanoscience and Materials of Aragon. So let me start by introducing the family of 2D materials. This family started in 2017 with the discovery of antiferromagnetism in iron phosphorus trisulfate crystals and intrinsic ferromagnetism in chromium triiodide. From this point onwards, there has been a rapid expansion in the number of members of the family, and in all the cases, there's a key ingredient, which is the presence of a magnetic transition metal ion into the lattice, giving these magnetic properties to the system. Nevertheless, the family still faces some important challenges, which are that the critical temperatures are still far away from room temperature for most of the systems here, and for the few exceptions that we can find within the family, they are mostly centrosymmetric, which means that they cannot hold some interesting properties, such as, for example, Jaroszynski-Mori interactions. So here in this study...
Jose, can you switch to presentation mode, maybe?
I thought I was in presentation mode, so let me see. Slideshow here. Are you?
Yeah, I think so.
Yeah.
No, we are not able to see it.
Okay. So maybe this way.
Yeah, I mean, if you are not able to switch to presentation mode, it's all right. Yeah, go ahead, please.
Okay.
I think he switched. He shared the wrong screen. I think he needs to reshare it.
Okay, let me try again. Stop sharing. Share again. Maybe I can share the whole screen and try again. So let me go through it. So now you are seeing the presentation?
Yeah, now we can see it. Yeah.
Okay, I'm sorry. So yeah, here we are looking for a magnetic material which has a broken inversion symmetry and which also has a high critical temperatures. So to address this first valid point of the broken inversion symmetry, we are going to look into the family of Janus transition metal decalcogenides, which are a family of materials which are inherently non-centrosymmetric because they have two different phases as the Roman god that gives them their name. In fact, this family gained a lot of attention in 2017 due to the successful synthesis of a molybdenum sulfur selenide monolayer. As we're interested in the magnetic counterparts of these materials, we have to substitute the non-magnetic transition metal ion by a magnetic one, such as, for example, here, as they did in this study, where they characterize a strong ferromagnetic behavior for manganese sulfur selenide monolayer. In this kind of systems, the interplay between the low-dimensional magnetism and the broken inversion symmetry gives rise to a Raspberry effect, and as we want to push as far as we can these exotic properties, what we do is to substitute one of the chalcogen atoms here by an halogen, thus increasing the electronegativity of the species and enhancing even more the Raspberry effect. In this last family of the Janus chalcohalides, also some theoretical studies have predicted promising critical temperatures, and that's where our material, the manganese tellurium iodine, belongs, and it's some kind of special member of the family because it holds an antiferromagnetic ground state configuration differently to most members of this family. So
Jose, can you see a pop-up at the bottom of your screen? You see like can you ocultar it? Like hide it? Thank you.
Okay, yeah, sorry. So now let me briefly introduce our theoretical approach here. So we will start by doing ab initio calculations in the context of TFT to compute the ground state properties of the system, and then through a process of linearization, we will construct a tight binding model where we can compute the energies of spin rotations and map them to a Heisenberg Hamiltonian. Through this Heisenberg Hamiltonian, we can carry out atomistic spin dynamics to compute some thermodynamic or macroscopic properties of our system. So let me start by characterizing the structural and magnetic ground state of the system. First of all, we compared several stacking periods, determining that this 1T ground state should be the ground, should be the geometrical configuration of our system. And then by comparing different magnetic orderings, we can state that the system behaves like under this collinear antiferromagnetic configuration, in which the local magnetization of the manganese atoms takes a value of 4.32 Bohr magnetons, which means that our manganese atoms have a spin configuration of S equals 2. Interestingly, under this magnetic configuration, what we have is that the lattice undergoes a distortion, so that the ferromagnetically coupled neighbors are farther away than the antiferromagnetically coupled ones. In fact, we can try to understand this distortion in terms of the octahedral environment of our manganese atoms over here. And what we have is that when we have this antiferromagnetic ordering, the octahedras undergo a compression along one of the axes. In fact, this compression has a clear effect in the density of states of our manganese atoms, because under the perfect hexagonal structure, the EG states and T2G states are completely degenerate respectively, but under the antiferromagnetic structure, we observe that the degeneracy is lifted. In fact, everything here reminds us of a Jan-Teller effect. So here I have plotted the evolution of the energy levels under this Jan-Teller octahedral compression, and let's check if our system has the same behavior. So we have to take this extended band picture, in which we can compute the centers of gravity of our orbitals, and we observe that indeed the EG states are higher in energy than the T2G states due to the presence of these peaks due to the hybridization near the Fermi energy. In fact, we can even resolve the EG states individually to see that the DZ states are higher in energy. Thus, our system matches this atomic picture of the Jan-Teller octahedral compression. What is left now is to assure that our system is dynamically stable. So what we do is to compute the phonon band dispersion and observe that we don't have here imaginary frequencies that might be a hint of a dynamical instability in our system. So we can say that our system should be dynamically stable. Now, in terms of the electronic properties, what we find is that we have some extended tellurium p states here crossing the Fermi energy, which means that our system behaves as a metallic antiferromagnet, which is interesting by its own because the pool of metallic antiferromagnets in 2D is still somehow limited. Now we can study the influence of the spin-orbit coupling in our properties of the manganese tellurium iodine. And first of all, in terms of the magnetic anisotropy energy, we have that the magnetization prefers to be aligned along this y direction here. And in fact, the behavior is also really interesting because the energy barrier between both perpendicular directions in the plane is way higher than the energy barrier between the y and the z directions. So here in these materials, we are out of the simple picture of an in-plane versus an out-of-plane magnet. Then we can even study the influence of the spin-orbit coupling in the band dispersion. And what we have is that when we turn on the spin-orbit coupling, we have a splitting of the bands. And for an isoenergetic level, for example, here, we can plot the spin polarization of the Sx and Sy components resolved in the momentum space, and observe here these clear helical asymmetries between both components, which are the usual hint for Rossby effect. We can even compute the value of the Rossby coupling parameter, which takes here a significant value of 0.39 electron volts angstrom. Now we can finally study more in depth the exchange interactions or the magnetic interactions in our system. And to do so, as I have mentioned before, we map our extended block states obtained from our DFT calculations to a tight binding model. So once we have this good agreement in the band dispersion, we can compute the energies of the rigid spin rotations and map them to extract the isotropic Heisenberg exchange parameter, which is plotted versus distance in this figure here. As you can see, the behavior seems to be a bit complex. So what we do is to plot here the spin lattice and observe that for the first neighbor, we have a strong antiferromagnetic coupling, while for the second and the third one, we have a strong two ferromagnetic behavior. So these three exchange parameters together help stabilizing this stripped collinear antiferromagnetic state. And even though we find some frustration into the lattice, it is not enough to revert the ground state that we have mentioned before. So, and this complex behavior with distance is kept in the system even when we consider different U values in our calculations, and even different calculations approaches, such as these KKR calculations carried out by our colleagues from the MPI Halle. And he obtained the same trend. And this difficult trend is nothing new for these materials, even though we have here an antiferromagnet, because for another member of the family, this manganese selenium iodine, this oscillatory behavior was also observed, and in fact, our calculations yield a good agreement with previous references. So once we are sure that our calculations are yielding correct results in terms of this interaction, we plug these exchange parameters in a Heisenberg Hamiltonian, where we will include two terms of uniaxial anisotropy that will help us stabilizing the magnetization in the y-axis. In fact, these terms will keep this constant ratio that we obtained from the magnetic anisotropy energy calculations that I have shown before. And here we can sweep for a wide range of these values, and in all the cases we can compute an L temperature for the system which lies close to room temperature. So just let me finish by completing our Hamiltonian with some of the missing terms in terms of the anisotropic exchange parameters, both the symmetric ones and the antisymmetric ones in the form of the DMI. And here, for this new set of calculations where spin-orbit coupling must be included, what we find is the same trend for the isotropic part of the Heisenberg Hamiltonian, but then we can even compute the strength of the Jaroszynski-Morilla interaction, which gives values which makes the system compatible with topological spin textures. And then we also observe the competition between the symmetric and isotropic exchange parameters, where the J, Y, Y components appear to dominate for most links, which means that this anisotropic exchange also favor the alignment of the magnetization in the Y direction. So just let me finish by computing again the Nernst temperature with the more complete Heisenberg Hamiltonian here, observing a slight shift towards room temperature lying here in this region of 300 Kelvin. So let me finish with my conclusions. We have observed this magnetically induced Jahn-Teller distortion, which is linked to the magnetic state in our system. Then we have a metallic character, and we can also see these Raspa splitting features. And finally, we have room temperature antiferromagnetism with strong DMI interactions. So thank you for your attention, and any question is welcome.
Yeah, thank you very much, Jose, for the nice talk. Is there any question in the chat? Okay, so maybe one question from my side. As far as I know, your results suggest that this material could support like chiral spin textures due to the broken inversion symmetry and strong spin orbit coupling, or?
Yeah.
Okay.
Yeah,
nice.
I mean, yeah, it does. And in fact, we are observing this a strong component of the in-plane Jaroszynski-Morilla interaction. So the system should be eligible to hold some kind of antiferromagnetic skyrmions or some kind of chiral structure here.
Okay, thank you very much.
Professor, I have some question about DFT calculation, some comprehensive results in my previous slides. Can you show?
Which one?
No, yes, no, you perform some comprehensive study by DFT and some webinar results. Can you show? Can you show all slides? No.
Which slide are you?
Actually, no, maybe no. Yes, no, yes, yeah.
Here? Yeah.
Yes. Here you perform some simulation work like DFT and like this Venner is also software or maybe some machine learning.
No, I mean, I perform this binarization in which you map your extended block states into a tight binding model, and it was carried out by this AtC-AtG program, which is well established in the community, and it's not based on machine learning or something like that for the moment.
The difference, some states near the Fermi level is by DFT or some like winners.
So here you have blue curves which are hidden below these dashed lines of the binary model. So I mean, we have here a perfect agreement between the energies extracted by both models.
And the magnetics movements are like magnetic. You can use in other picture by show arrow. You use potential U is 2. How can decide the exact value? I have a question about so.
Yes.
And this value exact by you can use potential like DFT plus U. How can decide the value of U?
I mean, for materials which are synthesized, you can extract the value of U from the gap from experimental measurements, but for these materials, which for the moment are not experimentally realized, what we did is to sweep in a wide range of U values and observe, for example, here that the behavior that we extract for all the cases is almost the same. So there is not a strong dependence with the U.
Thank you so much. Thank you so much.
Okay, thank you very much, Jose.